For this session, we're going to be talking about bivariate distributions and a little bit more about discrete distributions, including the topic of covariance. Now, we can figure out whether discrete random variables are statistically independent. That means you can vary one and it doesn't seem to have anything to do with varying the other, if the probability of some xy, so in other words, some set value of probability, given that, for example, if you remember our old problem where we had the first good part and the second good part, or the first part and the second part are both good. That's that joint probability right there. The way you could find out whether that is independent, statistically independent, is if this number, pxy, is the same as the marginal probability of x and of y, right? If these two values are actually, when you multiply them together, if they become the same as this value, then you know you've got statistical independence. So we can try that. We'll whip out our handy dandy calculator and we'll take 0.875 times 0.875, right? These two things multiplied together, and it's 0.765. Wait a minute. It's not quite the same. So even though it's quite close, which indicates that they're pretty independent, they're not identical, and so they are not actually statistically independent. So we're going to explore these ideas in more depth. But first off, let's go over a little bit about how we can calculate the expected value of a function that depends on two variables like x and y. The way we would calculate that, if you'll remember, our old way of calculating the expected value was simply to round up over all the x's. We would take x times probability of x, do that for every value, and hey, we've got the expected value. Here we're doing pretty much the same sort of thing. We take, well, expected value of that particular function, so that's sort of like the idea of x, and then multiply it by the probability of the function itself, or the probability density function at that particular point, add everything all up, and you get the expected value of that particular function. If we've got a random variable x and y that's continuous, then all we'll need to do is do a double integration of the function times its density function over that particular area. And we'll give some examples, and it's nothing ugly at all. So if you haven't had these kinds of things in calculus yet, not to worry, we'll show you how to do them. Now, a neat little trick is that if you have an x and a y that are statistically independent from one another, means you can vary one and it doesn't affect varying the other, then the expected value of whatever that function of x and the function of y is actually, you can sort of dissect it and take it apart and just have the expected values of each of those functions multiplying themselves. So then also for any random variables x1, x2, blah, 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 they do not need to be statistically independent. If you take the expected values of each of those random variables, well, you can add them all up individually so you can either do it inside and then take the expected value, or you can do the expected value of each of those independently and add them all together. Also, as you might expect, the expected value of the difference of two variables is just the expected value of the first variable minus the expected value of the second variable. Now let us look at a very handy formula which says that if we want to calculate the variance for any particular function, the way we would do it is, well, you've got this formula here, the first one, but really you want to use this one. This is pretty much along the lines of what we saw earlier, where we could calculate the expected value by going like this, right? Or calculate, sorry, the variance of some x. This is the same formula, essentially, but now made for a function of two variables. Now, if we have a bunch of random variables that are statistically independent, then we can say that the variance of each one of these all added together is equal to the variance of each one taken separately. And also, if x1 and x2, for example, are statistically independent, then the difference is actually the addition of each of the variances taken independently. So this allows us to calculate a special property, and what that is if we want to, let's suppose that we have some normal random variables, so they're characterized by a normal curve with a mean and a standard deviation, and we can have these random variables, that's x is characterized by that kind of normal curve, and y is also characterized by a normal curve. It just has a different mean and just different standard deviation. And let's say those two random variables are statistically independent. Then we could say that there's a new random variable, which is simply the addition of those two random variables. And this one is also going to be a normal random variable, and its mean is going to be the addition of the two means, and then the standard deviation, as you might expect, is calculated simply by taking the addition of the two squares and then the square root of that. And we could make this a more general formula by using this methodology right here, and that all makes good common sense. So let's work a problem that applies exactly this idea. So for this particular example, we have a plastic casing for a magnetic disc, and it has two halves. The thickness of each half is normally distributed with a mean of 2 millimeters and a standard deviation of 0.1 millimeter. The halves are independent. To determine the mean and standard deviation of the total thickness of the two halves, that's for part A, so let's work that. We can say then that, well, we could call the thickness is just going to be x plus y, right? So that would be the total thickness. And then we could say that the expected value of that thickness is just going to be the addition of the two expected values. Each one is 2 millimeters, so it would be 4 millimeters. So then the variance of that thickness is just going to be, take the variance of each one independently, so this one squared plus this one squared, and that's 0.02 millimeter squared, and then that's going to mean that the standard deviation of that thickness is just the square root of that, which is 0.01414 millimeters. Right, so that's just the square root. And now for part B, they want to know what is the probability that the total thickness exceeds 4.3 millimeters. So for that, we're looking for probability that t is greater than 4.3, and so that means essentially we're looking for the probability that z is greater than Well, plugging into our formula, remember our formula is z is equal to x minus mu over sigma. .3 minus 4 all over 0.1414. In other words, the probability that z is greater than 2.12. So that's going to give us, looking at this, if we look at the chart, get 2.12 and this is 0, so it actually would probably be further out, more like here. Okay, so what we're going to look on the table to find for z is equal to 2.12. So we go and take a look at our tables. 2.12 is what we're looking for. So I just happen to have a table here. And we go to 2.12. See, let's look up here at the top just so you see. Here's the z, I'm looking for 2.12. So we're going to be going over to this particular column. And we need there's 2.1, 2.10, 2.11, 2.12. So it's 0.9830. 0.9830. Now what we're actually looking for, though, is something just a wee bit different. We're looking for the probability that the total thickness exceeds 4.3 millimeters. In other words, we're actually looking for this area up here. So clearly that would have to be 1 minus 0.9830 is going to be the probability that z exceeds 2.12, and that number will be 0.0028. So that's the probability that the total thickness exceeds 4.3 millimeters. So now all we've done so far is we've covered bivariate distributions, and we've been basically just applying existing concepts, probability density functions or expected value, to bivariate random processes. But now, oh boy, we get to introduce a new concept. But the essence of this new concept is you've already seen it a million times in all sorts of other situations, so it's not like it's really going to be all that new. We're going to talk about the idea of covariance. So if you consider a random process that has these random variables x and y, you collect several samples from the process and make a scatter plot. If the covariance is positive and large, you're going to see something that looks along these lines, right? You know that as you're generally increasing x, you will generally see an increase in y. If the covariance is near 0, it's going to look like this, and that just means basically that there's no real relationship between x and y. And then also you can have something where a covariance is negative and large. That means that you vary one way, well, the other one varies very strongly but inversely. So the covariance between random variables, you can calculate it by using this formula for the expected value. An alternative formula is this one right here, which is actually a little easier to use, and we're going to do a sample of that later on. So then a definition and property about these is if you take the expected value of x and y and it's equal to ex times ey, then that covariance is 0. So we saw a little of that earlier. The converse isn't necessarily true. Now notice that if you have random variables x and y, then if you add them together, right, then you can calculate the variance using this equation right here. The problem with covariance is if you do have something large, positive or negative, whatever it is, it all depends on the random variables x and y as to how large that actually is. So you can find a way to eliminate this problem by just using the idea of a correlation coefficient. So we take the covariance and then divide it by sort of a normalizing coefficient right here, and that gives you the correlation coefficient. So correlation coefficient varies between -1 and 1, and it has the same sign as the covariance. So let's take a look at this applet right here. Now we can have our correlation coefficient and our number of plots, or our number of samples that we're going to test here. Let's see. Let's make a strongly correlated. Well, we can actually use this guy here. We're going to make this positive. Okay, it's got a 0.71. Notice how these dots relate to one another now. If we increase it all the way, look, if it's a perfect 1, then we know that as much as we might increase x, y increases exactly the same way. And then likewise, we can go kind of back through here. Notice they don't look affiliated at all. Go all the way back, and now, wow, now they're negatively correlated. So this is just a neat little plot to show you the relationship between these various correlation coefficients and how the data actually look in comparison with one another. Now for this problem, we are asked to determine the covariance and the correlation coefficient with the random variables for that previous good-bad part example, where we already found that it's not statistically independent because this value is not the same as when you multiply these two values together, right? So when you go off to the end, the edges of the earth to the marginal distributions, and multiply those puppies together, they're not equal to this. So the way we would calculate the covariance first is we look at our formula. We always have formulas for things. It makes things so much easier. The covariance is going to be EX Y minus EX EY. So that's our very easy formula to use. Now we can calculate the expected value of x, and we use our usual formula. We take the value itself times the probability of that value, so that x is equal to 0, right? The probability is 0.875, and then the probability that it is 1 is 0.125. So all of that is 0.125. And the expected value of y is just, let's see, 0 times 0.875 plus 1 times 0.125 is equal to, by golly, the same thing, 0.125. So now we've gotten these two values figured out, and the only one we still need to figure out is this one right there. How do we calculate that? Expected value of xy. Well, that is simply the sum over all the x's and over all the y's of x times y, times the probability of x, y. And so that is, well, we got to just do each one individually. So we're going to take, let's see, this particular value is that probability when x is 0 and y is 0 is 0.764. And then the next one is going to be, let's see, x is 0, y is 1. So 0 times 1 times, and then the probability there is 0.111. So 0.111. And then just kind of keep doing that. 1 times 0 times 0.111 and plus, let's see, can I squeeze this in here? 1 times 0.014. And when you add that all together, it's 0.014 because we have a lot of zeros in there. So next, we're just going to plug in, say, covariance xy, or x, y, is expected value of xy minus each of those expected values multiplying themselves, and that is just 0.014 minus 0.125 times 0.125, and finally, last but not least, that becomes minus 0.002. So now, does this actually make sense, right? Or even more importantly, how can we begin to understand this? Well, the best way probably is to continue on. We've got the covariance, and what we really want to get now is the correlation coefficient. So we're going to have to take this guy and magically swap it out with our new formula for our correlation coefficient with a nice clean slate here so we can start working. And what we need is this covariance value, which we've already calculated, but now we need these new variances. So let's go ahead and calculate each one of those. All we need to do is apply this formula. The variance of x is equal to the expected value of x squared minus squared value of the expected value. So we'll calculate the expected value squared, and all we'll do is take the value itself, 0 for example, x is 0, times the probability. So we take that value, square it, and do that for both 0 and 1, 0.125, and that is 0.125. So then we can calculate the variance of x. We're plugging into this formula right up here, this variance of x. So it's going to be expected value of x squared, which is 0.125, minus the squared expected value. And this would be, remember, just expected value is just going to be 0 times 0.875 plus 1 times 0.125. So it's just going to be 0.125, and we need to square that. So it's 0.125 squared. So we're subtracting, and then we find it 0.109. Now, likewise, if we pull the same trick and look at the expected value of y, squared is going to be just 0 squared, 0.875 plus 1 squared times 0.125, and that's going to be 0.125 again. And just as we did before, of y is going to be 0.125 minus 0.125 squared, and that's 0.109, just as we might think it would be. And so now, plugging into this equation, which I'm just circling in green, we can say the correlation coefficient is covariance of x, y, over the square root of the variance of x, square root variance of y. That is just going to be minus 0.002 all over square root of 0.109 and square root of 109. So when we multiply that all out, it becomes minus 0.018, and that is our correlation coefficient. And if we pause and ask ourselves, do these values actually make sense? Well, they do. What they're really saying is this correlation coefficient is really darn close to 0. That means they are those two values, the x and the y that we saw for those parts, are really almost completely independent of each other as far as when they vary. The other one, you can't make any predictions about what the other one's going to be doing. But there's a tiny bit of relationship, and that's what this non-zero number right there indicates. So earlier we saw that with this particular problem, the x and y were statistically dependent, but not by too much. They should be, these values should be near 0, and indeed, that's what we found.
That's all, folks.